Hello everybody, welcome back. Today we're going to be doing 5.6 properties of linear relations. In this section we're going to identify and represent linear relations in different ways. Let's make a connection here. I think we all say we probably enjoy pizza. The table of values in the graph shows the cost of pizza with up to 5 extra toppings. So in this particular pizza store, the number of extra toppings is given in the x values, and the cost depends on that. So the independent variable is obviously extra toppings and the cost. So I don't know what the toppings are already there. We're not sure. But for each each additional, I should say, topping, you can see that it's increasing by 75 cents. So it's $12 for 0 extra, 1 extra, $12.75, and so on. You can see a pattern. And this is a linear relation. Okay, in this case, a linear function. So a little break in the graph, just starting out at $10, and it's increasing by 50 cents each time here. That'll allow you to do your 75s, and then the horizontal, or the x values, are the number of toppings. Okay, so you see a pattern, right? It's increasing by 75 cents for each topping. All right, and you would have done different patterns like this in middle school and elementary. Now we're going to put it into a function form. Okay. So another one is a rental car. So some rental agencies, there's a fixed cost. So you rent the car at $60 regardless. And then for every 100 kilometers you drive the vehicle, it's an extra 20 cents. Or sorry, $20. My apologies. The independent variable is the distance driven, and the dependent is the cost. So the cost depends on the distance traveled. Okay. So the independent variable going up by every 100 kilometers. It goes up $20. Okay. So again, remember we can represent this as an ordered pair. So x and y, right? 0, 60, and 180, and so on. So both your x and y values increase by the same amount. Now they don't have to both be the same, but if your x goes up every time by the same amount, so 100 each time, and your y values go up by the same amount, 20 each time. They don't have to be the same, obviously. This is what's called a linear relation. And in this case, a linear function. Okay? There's a graph we just draw. So independent variable, distance in kilometers. Dependent variable, cost, right up the y-axis there, cost in dollars. The change in the dependent variable over the change in the independent variable. So this is what's called rise and run. Okay? Change in x over change in y divided by the change in x. Rate of change. Rate of change you'll take with you through all the courses that you do. Okay? We can use each representation above to calculate the rate of change. Right? So there, when I talked about, I said 20 cents per kilometer, 0.20. I did the division already. All right? So the rate of change is every kilometer you drive, it'll cost you 20 cents. Okay? That's what that means. So the equation we create is cost. So your equations are always going to look like this. Your dependent variable, so y, is equal to your rate of change. This is called your slope. We'll talk about this again during these sections, the next two sections, in the next chapters as well. The rate of change, it was decimal 2. We got that from the change in dependent over the change in independent. So change in y over the change in x. The independent variable is multiplied by that change, and then the initial amount, what it was. So when D was 0, it cost 60, right? $60 regardless for the rental. Okay? Let's look at an example. Determining whether a table of values represents a linear relation. Which table of values represents a linear relation? Justify your answer. So let's take a look. So in Celsius, the Celsius is going up by 5 each time. And the Fahrenheit is going up by 9 each time. Therefore, you do indeed have a linear relation. In B, the relationship between the current, I amps, and power, P in watts, and electrical. Okay? So, the current, I, is going up by 5, and the power is going up by 75, and then up by 225, and then up by 375, and then up by 525. So this is not a linear relationship. Remember, The x values have to go up by a same amount, and the y values have to go up by a same amount. They both don't have to be the same, but they, like, it doesn't have to be the same on either side, I guess I should say, but it has to go from each on to the next value. This is called a common difference, and it has to work on both. It did for I, but it didn't for P, so it's not linear. It did for C and F, so it is indeed linear. And I'll write that in for you right now. So as I mentioned before, this is just a justification. You're showing the difference in values, and this is called common difference. So the common difference here was 5, the common difference here was 9. Therefore, the difference is constant in both, so it is linear. Here we had I was constant, however P was not. So therefore, this is not a linear relation. Both columns, x and y value changes have to be the same. Change in independent and dependent both have to. So there's a check your understanding question that goes along with there, and there's the answers, and there's the graph as well. Okay? And just a little remember, when the equation is written using the variables x and y, x represents independent, y represents the dependent, like I showed before in the equation. Okay? Very important we recognize that. Example number 2, determine whether an equation represents a linear relation. Alright, so this equation here, we have y equals negative 3x plus 25. So we'll pick some x values, and we'll substitute them in, and we'll solve for the y values, and we'll see what we obtain. Okay, and you can just do this on a piece of scrap paper as you plug them in. So I'll start off at negative 2. Oh, negative. Usually like to have some negatives and some positive values. Once you start to do these, we'll get the hang of this. All right. So there are your x values. All right. So you just pick any values. They weren't there. You just pick values. Like I said, usually we look at your equation to determine those, but you'll get those. We'll come with practice. So we'll put these in. If I put a negative 2 in here, negative 2 times negative 3 is 6. 6 plus 25 is 31. So I'm substituting the x value and calculating the y. If I put negative 1 in there, I get negative 1 times negative 3. I get 3. 3 plus 25 is 28. Oh, sorry, 28. If I put 0 in there, it's obviously 25. 0 times negative 3 is 0 plus 25. If I put 1 in there, I get negative 3. Negative 3 plus 25 is 22. If I put 2 in there, I get negative 6. Negative 6 plus 25 is 19. Okay? So those are the corresponding y values to the x values used by the equation. You'll notice that these go up by 1, so there is a common difference of 1. These go down by 3, so there is a common difference or a constant difference, right? So this indeed is a linear relation. Okay, so to graph that, I've provided you with some graphs, and I'll do those with you in class. But for now, I'm just going to get the graph from the textbook for you. So I showed it via a table of values, how you determine whether it's linear or not. But graphing it, so I plotted the points, and there it is. Right through. Next one we have is y equals 2x squared plus 5. So I'll graph this one here. I'll use the same x values that we did in the previous question. All right. And then corresponding y values. So put the negative 2 in. Negative 2 squared is 4. 4 times 2 is 8. 8 plus 5 is 13. Next one is negative 1. Negative 1 squared is 1. 1 times 2 is 2. 2 plus 5 is 7. Put 0 in. 0 squared is 0. 0 times 2 is 0. 0 plus 5 is 5. Put a 1 in. 1 squared is 1 times 2 is 2. Plus 5 is 7. You're getting the same value back because you're squaring a negative, so this would be 13. If you were to guess that, you'd be correct. But 2 squared is 4. 4 times 2 is 8, and 8 plus 5 is indeed 13. Okay, so the x values do go up by a constant amount of 1. The common difference is 1, but the y values, they go down by 6, then down by 2, then up by 2, then up by 6. So clearly not linear. All right. So this one here, I guess I should say, was linear. We use that based on the table of values and the graph. Okay. Now, if you were to plot this graph right here, this is what it's going to look like. So this is it's either we say not linear or non-linear, either's fine. The textbook, I'm not sure what they exactly say. So it's not a linear relation. So not a linear relation. Okay. And I'll grab that graph now. So if I were to graph this function, this is what it would look like. You'll see that it's clearly curved. We're going to learn about this in Math 11 next year in September. So this is what's called a quadratic or a parabola. We'll leave it there, but obviously if it's not a straight line and it can't be connected through with a ruler in a straight line, is not a linear relation. The next one is y equals 5. So that means the y values are always going to be 5. And it doesn't matter what you pick for the x values. You can pick the same ones as we did before. It's not going to make any difference. Okay? What you pick. I'll go 0, just to be consistent with the textbook, I'll go 0, 1, 2, 3, 4. It does, but I said, it doesn't make a difference because the y is always equal to 5. So this is actually a horizontal line that goes directly through your graph. Okay? So I'll show you what the graph looks like based on the textbook. So you can see if you plotted 0 and 5, 1 and 5, 2 and 5, 3 and 5, 4 and 5, you can clearly see that it is linear. And also, looking back at I, this is not only a linear relation, it's also a linear function. And same with this is also a linear function because you can draw a vertical line and that doesn't connect at any 2 points, right? Now let's look at the fourth example here in 2a4. X equal to 1. So that means all these are all 1, right? Okay. So in this case, there's nothing to solve for in y, so they can literally be anything. So I'll just pick this. You can pick whatever x values you want, or whatever y values you want. The x values are always going to be 1. Okay. So this is an interesting situation too, where it is a straight line, it is a linear relation. You can't, the common difference is 0, so it still counts. You're probably saying, oh, well, if you look at the table of values, what you said before, but it is, the difference is 0. So it's still, and these do go up by 1, so it is a linear relation. But it's, however, it's not a function, as you're going to see in a minute when I put the graph in. Like I said, it is a linear relation, but it's not a linear function. As you can see from the graph right there. Obviously, it's a linear, but it's not a function. Okay? So it says, which equations of part A represent linear, and how do you know? So I've already answered that as we went along. Okay? And I'll put the blurb that I have in the textbook as well for you. So, like I mentioned in the last few minutes, the graphs in parts I, and I4, so first, third, and fourth, I mentioned our linear relationships, they have straight lines, and obviously the second graph did not. You can see it was clearly curved. All right, so to check your understanding, I'd probably recommend doing the Scribbler just with the interest, there's not very much room left there. Okay, so in the next video, we will start back at example 3, and we're going to finish the section 5.6. So thanks everybody for watching. I hope the videos are helping, and we'll talk again soon.